Welcome to my talk on X-by-Construction and how we envision integrating non-functional properties of software quality into by-construction engineering. Very complicated title, and before we get to what by-construction engineering is, I want to thank my co-authors, Tabea, Alex, and Ina, for contributing to this paper. We're going to have a look at a major concern that every developer, every software developer, probably all of you, somehow face when you develop a program, and that is software quality. And if I would ask you what you connect with the term software quality, I would assume that this is correctness. Your program should do what it is intended to do, but depending on the domain you are working in or you are developing a program for, there can be different focuses. All of them have in common that software quality is important. Otherwise, your program will fail. There will be costs, consequences, maybe even endangering human lives. But software quality is not only about functional correctness, but also other properties. This is from the ISO 25010 standard. They define software quality or software product quality in 9 different properties. On the left, you can see functional suitability. That is a bit weird. I will call it functional correctness in this talk. But this means exactly the same. And we have 8 different non-functional properties that are split into sub-properties that describe the main property. Usually, correctness is still important, and the main driver as a program that is not doing what it is intended to do, but is maybe very safe, is still of no use. So your focus is usually on functional correctness. And functional correctness is commonly ensured by testing. That is probably what all of you would do when you start developing something. But as we heard, I think yesterday in some talk, also Dijkstra said that you can show the presence of bugs, but not their absence, as you can't test all the inputs. An approach to actually guarantee that a program is working as intended is formal verification. And for those of you that attended, I think it was the first keynote on Thursday, that might know a bit about formal verification, and for those of you that didn't attend or don't remember, just a small recap, what is that? Formal verification is an approach to guarantee that a program is working for all possible inputs and is based on logics and mathematics. We prove our program according to a formal specification and check whether the program fulfills this specification. Common approaches are model checking and deductive verification, and those two and also other approaches have in common that they are applied after you actually implemented your program. So you have 2 parts, your implementation and your specification, and then you have some nice tool, hopefully, or you do it by hand, and prove that those 2 fit together and your program actually fulfills the specification. The approaches where you have both before starting verifying are called post-hoc approaches. So they are only applied after you are done with your implementation. An alternative are so-called, or is, correctness-by-construction, in short CBC. This offers advantages because you can start verifying earlier, so you don't have to complete your whole program to start receiving information on whether what you did is correct or not. CBC is a refinement-based incremental approach and is based on the formal specification. So for post-hoc approaches, it would be possible to write your program and your specification 3 weeks later. This is not possible for CBC. You have to write your specification first because based on the specification, you apply different refinement rules. Refinement rules represent basic programming constructs like selections, loops, assignments, method calls, and so on, and are applied on an abstract program that you want to concretize to an actual concrete program. And the nice thing about CBC is that you can verify each of the refinement steps. So each refinement rule comes with so-called side conditions that you can check. And if this check, or the verification, is successful, you know, okay, this application was valid and still fulfills the given specification. And in the end, the result is the same as in post-hoc approaches. That's the correct implementation, in this case, even correct by construction. As a summary, advantages, we still have proven correct programs as in post-hoc verification, but we get earlier feedback on the correctness of our program. And also, if a proof fails, we already know at what point in the program we have to look for a bug. In post-hoc verification, you just know, okay, at some point in the program, there's a problem. But as we have a very fine-grained verification, we can already localize the bug very easily. So how is that looking in practice? Okay, forget the second point, that shouldn't be there. We start with a Hort triple PSQ, where P and Q are our pre and post conditions, the specification, describing the intended behavior. And in this example, we want to implement a searching algorithm. So we have a precondition that just says, okay, we have some array A that should be initialized and contain at least one element. And we have a post-condition Q that says if there is our element X that we're looking for in this array A, then we want to have some pointer or pointer I in the end that points to this element we are looking for. And now we can start applying refinement rules. For the first one, we would apply the composition refinement rule that just splits our abstract statement S that we want to implement into two, because otherwise we could just like apply one assignment or one loop, but nothing else. So for now, we would apply the composition rule, which comes with a side condition, which sounds like we need to be able to define an intermediate condition, in this case M, that is valid after executing the first statement S1 and before executing the second statement S2. So basically, we split our single abstract statement S into two. And then we can continue with, for example, initializing I to the last element of our array and creating a loop with a loop body that iterates from the last element to the first in our array until we found X. And in this tree, we can verify each of the nodes individually and in the end have a correct program. So back to software quality, we can ensure functional correctness using CBC, and there are approaches for all the other properties as well. I'm pretty sure for all of them, maybe almost all of them. What they have in common, as for post-hoc verification, usually they are applied post-hoc. So you have to implement your program first before you can start ensuring, proving, whatever, your non-functional property. And the question is, or the problem is, that you only get that late feedback. Your program might even be deployed because you have like a deadline, and you figure out, okay, my software for some plane or healthcare is already deployed, but I didn't ensure other properties. And we ask ourselves, okay, why not combining the advantages of CBC with the early feedback also with non-functional properties? And previous colleagues of mine started doing that for security. And there are two techniques that are a result of that work. That is confidentiality, C14BC by construction, and information flow control by construction. Both of them fit to the security property in the table you just saw and ensure information flow policies. So we can, for example, ensure that a high security variable is not leaking information to a low security variable through both direct and indirect information flow. However, those two are the only ones and are referred to as X by construction. So the summary of techniques for non-functional properties in by construction engineering is XBC. The X in this case is a random non-functional property you could put in there. However, those two is the only work that happened so far, and that is why we thought, okay, let's have a look on the other properties that are still there and not covered yet. Resulting this gap, we thought of our vision, and that is also what our paper is mainly about, how we imagine extending XBC and by construction engineering to cover further non-functional properties, to have like a programming paradigm for high-quality software. Still, functional correctness should and needs to be the main driver of program construction. As I said earlier, a program that is not doing what it's intended to do is of no use. But we imagine flexible and customizable integration of non-functional properties in your development process, always depending on your use case. Maybe you have a program where you say, okay, that needs to be fast, but I don't care about security. I don't know if that's clever, but anyway, you should be able to set that focus. Also, we want to maintain as abstract as possible. So we don't want to have, or we want to have as few as possible dependencies to the remaining structure of our system and also the hardware that our program might run on later on. And finally, also to maintain usability, we imagine some kind of tool support for CBC and also the existing techniques of IFBC and C14BC. There is tool support, which should be extended and made be usable. The result, as I just said, should be a paradigm to be able to create high-quality software, not only for ensuring functional correctness, but also non-functional properties. And we said ourselves, okay, we have a vision now. Where should we start? There's like a wide range of properties that one could cover, as you've seen before, and we decided to look at them and see which of those are likely to be integrated into XPC and which are maybe a bit more difficult. And based on the existing work, we defined 6 requirements where we think that they need to be fulfilled to be actually able to integrate a property into XPC. The first, and that is the starting point also for CBC, is somehow a specification. We need to be able to define how this property that we want to integrate should look like in the end. For functional correctness, it's just the specification, the functional specification. For IFBC, for example, we can declare what variables have what security type, and this needs also to be possible for other properties. Yes, as I said the slide before, in our vision, we want to be as abstract as possible for 2 reasons. We don't know the structure of our program because, we just didn't start implementing it yet. And also, we want independence between other properties. So you could say, okay, maybe a program is really quick but consumes a lot of energy or is not safe anymore. So there will be interferences between certain properties, and we want to maintain either independence of them. That won't be possible in all cases, but for the cases where it is not possible, we want to have some rules how to handle them. The 4th requirement is that we somehow need to be able to check if our property and the specification that we defined earlier is fulfilled or not. The 5th requirement, and that is one that is applicable on multiple levels, is compositionality and modularity. We have 2 points. We have like the program itself that you saw earlier, and the program in the CBC tree, where we can say, okay, we only have a part, but we need to be able to reason from the part of a program to the whole program, and we have compositionality on the whole system level. So if you imagine energy consumption, we'll have a look at that later, there are dependencies outside the program we're just constructing. There's a whole system, there's hardware. And finally, the last requirement is the combination with the refinement tools that are existent in CBC, which are the main driver, which need to be able to somehow fit, or the new non-functional property needs to be able to fit into those rules so that the non-functional property can be assured on the side while using the refinement rules of CBC. And we assess the properties that you saw earlier on the table, whether those requirements are fulfilled or not. And you'll see a table with the properties on the left, the requirements on the right, and whether they are fulfilled or not. We did a bit of literature research, and you will see that there are like check marks and also check marks in brackets. The ones in brackets are, let's say, partially fulfilled, or certain of those sub-properties you saw earlier are fulfilled, but not all of them. Those 2 are already existent in CBC and IFBC for correctness and security, and you can see, as we all expected, that the requirements are fulfilled here. For performance efficiency, so that is time, memory, energy, and so on, we can also fulfill the requirements, some of them under certain conditions, and the same for reliability. For safety, compatibility, and maintainability, it's a bit worse. So those 3 are currently not planned to be integrated into XPC. And for those of you that have a very good memory, yes, there were 2 more on the table. That is flexibility and interaction capability. We didn't assess these because they are too far from the actual code level that we are looking in CBC, but more on, let's say, management level. So we didn't assess them in this paper. Based on the results, we decided to have a look at performance efficiency first. And as we are in a world where there's climate change and sustainability, we decided to look at energy first. The ISO 25010 in this term says energy efficiency. For us, we look at energy consumption, so the actual energy that our program might consume when running. And now you might think, okay, we are on a program level, and I just said we have dependencies, and yeah, to both the system, the remaining system, and also the hardware we might run our system on in the end. That is why we said, okay, we have ideas, but this is not like a final concept, just a starting step towards integrating energy efficiency into XPC. And there is like a kind of gap. As you might imagine, we have like high-level code in CBC. So our tool produces Java code, and yeah, depending on your compiler, your hardware, there will be different energy consumption. So you can't just like map the Java code to a certain energy consumption. That's why this is all just like a sketch. There will be some hardware model later, but don't take that too serious for now. The first step, as I said earlier, we need to have some sort of specification for energy. And we want to stay abstract, so it's kind of hard to actually say, okay, how would that specification look like? We had different ideas of having concrete values. Our program should maybe, as an upper bound, consume 5 joules. We could say, okay, we have intervals, like 3 to 5 joules, or we could go for an approach like in information flow control by construction, where we have different levels of high, medium, low energy consumption. For now, we decided for abstract, uninterpreted symbols that somehow, it says count, I don't like the word, but still count the energy that is consumed in our program. And those symbols, there are 4 of them, for writing, reading, binary operations, and returning variables. Those 4, we chose them because they fit our use case. There's no other reason for that. And yeah, we want to step through how this process would look like. And this is the same that you saw earlier for linear search, so it looks a bit different, but in the end it's almost the same. So the Hort triple PSQ extended by some energy annotations. So in our precondition, we say, okay, we don't want to have any energy consumed yet. You could say, okay, there will be energy consumed in some prior program state, but we don't look at that now. And for the postcondition, as I said, it's hard to specify what energy will be consumed because we don't know how our program will look like. That's why for now we're more like in a tracking mode instead of actually specifying it beforehand. So for now we say our postcondition or our energy annotation in the postcondition is undefined because we don't know of the structure yet. And now we can start doing the same that we did earlier, apply refinement rules. In this case, we would again have that intermediate condition that needs to be fulfilled after S1 and before S2. And we have the same here in blue. Our intermediate energy annotation is undefined for now. But as soon as we have the assignment on the left where we initialize our iterator variable, this undefined becomes concrete. So for the operation or the assignment of the subtraction of the length of array A minus 1 to variable k, we can say we have 1 reading, 1 writing, and 1 binary operation, or the energy that those operations consume. And the same is happening on the right side for the loop. Don't be confused. That method or that implementation is extended by a return value. That's why the tree is slightly bigger than the one that you saw earlier. And the more we implement, the more of the undefined energy annotations become actually concrete. And you can see now in the end, when the program is constructed, our postcondition is also not undefined anymore, but we have the concrete energy consumption of the whole program. And now the question is, what can we do with that stuff? One could say, okay, yeah, that was possible before. We don't need CBC to actually get that term up there. But the nice thing is that with those fine-grained energy annotations, we can work with families of algorithms. Think of sorting or searching algorithms you have a lot of implementations. They all produce the same result, but have a different structure. And one could start now, okay, implement different, for example, searching algorithms with CBC and compare parts of them. There are similarities, and one could figure out, okay, algorithm A takes less energy in this part of the algorithm than for algorithm B, and maybe improve one of them. Yeah. Another direct application would be to put in values. As I said, there's somehow a gap between our high-level Java code and the actual hardware we would run on. However, we jumped over that gap and mapped our energy annotations, the 4 on the left, to concrete values for hardware for PTX, or hardware model for PTX instruction level with concrete values, in this case in nanojoule. And now we could say, okay, we take the energy consumption or the energy annotations of linear search and also for second implementation of binary search and initialize them with the values of our energy model. This would look like this. You would expect for linear search, we have some linear energy consumption, and for binary search, it's logarithmic, as we split the array always in half. And now, we can put that in a diagram. That is what you would expect. Blue is linear search, and green is binary search. And if we look at it closer, we can say that for array length between 0 and I think that is about 12, linear search consumes less energy than binary search, and from that point on, binary search would be more efficient. I already mentioned some of our challenges and especially limitations of the approach you just saw. So we have that limited expressiveness because of this gap. We saw that just in the keynote this morning, so different abstraction layers might be some approach here. Also, the dependencies to system and hardware that I mentioned earlier. For all non-functional properties, not only energy efficiency, but also the remaining ones, we have the modularity and compositionality issues, as most of them can't be looked at completely local. And finally, we still want to be able to apply this in practice. So what you just saw with the energy annotations, that could be automated kind of quickly, but the true support for that is not there yet. And when you think about having more non-functional properties and having these interferences that I mentioned in, I think it was the third, we somehow need to be able to make that usable. Yep. So what are we doing now? Currently, we are refining the idea of energy annotations and formalize them. Like, this is a formal methods topic, so somehow we need to prove that what we are doing is actually true. This concept is called energy efficiency by construction, and maybe you'll read something about that next year. We are looking at closing this gap between low-level energy models and our high-level programming language by looking at Pancake, a language mainly used for developing drivers, so hardware closer. We're also looking at reliability. That is because reliability also fulfilled the requirements that we saw earlier. Now you could say, okay, we have a program that is already proven correct. How should that not be reliable? We are abstracting from the program level to a component level. So imagine you have components that are constructed using CBC or some other formal verification technique, but there might be components that you didn't verify, that are maybe just tested or even learned components. How would that look like? And finally, the other performance efficiency properties, memory time, and so on. Yes, and again, to support. And with that, maybe the most detailed look on software quality you ever did. I showed you CBC and hope you got an idea on why this is a nice idea, and also presented our vision. And we had a look at first ideas for energy annotations. And with that, I'm done. Thank you for your attention, and I'm really open to answer questions.
Please go to the mic. Thank you. Thank you for the cool talk. I'm really wondering, so with the, thank you. So for this energy efficiency by construction thing, I'm curious to see how you've sort of separated it from like some sort of hardware and architectural concerns, even though you instantiate with like the energy constants for PTX instructions at the end. But I feel like my understanding of a lot of this efficiency and energy consumption also relies on things like size, structure of cache lines, and also as we're talking about like the most energy consuming programs running right now are machine learning workloads. Those are running on like vector machines, GPUs, and like some of these more like specific machinery. So do these constants still hold meaning, or is this like extensible to accommodate these kinds of architectures?
No, that is a very abstract and basic idea. So we didn't take those into account. But that is what is happening in the current work, so that we somehow take those dependencies into consideration. I mean, the mapping of the PTX instructions and our energy annotations, that is very easy and too easy. That's not how it's happening in reality. So yeah, that is part of ongoing and also future work.
Cool, thank you.
Hey, thanks for the talk. So I was wondering, like, could you say that the energy annotations are like a more precise way to determine the complexity of an algorithm, right? Because normally we discard the constants and the smaller, factors.
Yeah, I mean the complexity was kind of the result that you saw when we did the instantiation with linear and logarithmic consumption, and that is also what you would expect in complexity theory. The fine-grained part is kind of the core of by-construction engineering, that we don't look at the whole program, not only in functional correctness and not only in the energy annotations, but in all properties.
Right. So the complexity would be like a lower bound, probably, right, on the energy? Something like that. Okay, thanks.
So wondering, you had this table of all the different quality metrics you could be interested in, and then it was kind of a sad ending that most of them we can't do in this correct by construction thing.
Yeah.
I think maybe if we move outside of this sort of triple kind of strategy for correct by construction, there may be some ways to get some of the CBC benefits for the other rows, or how do you think about that? Is it just a lost cause?
Yeah, so that is kind of addresses the point of reliability that I mentioned on the future work slide. At some points we are not on program level anymore. Yeah, so we need to go on a different level, either component level, maybe for certain properties even on system level. But that is something that we didn't focus on in this paper, but that might definitely be something to look at.
Thanks.
Okay, we seem to be out of questions, and I think we're bang on time. So let's thank Max again for a very interesting talk.